Okay, so welcome everyone from me as well. As Beth already mentioned, this is the last event on the GloBIAS seminar series for this year. And we welcome David, Kimberly, and Ruaridh from University College London. This is actually part of a new mini-series. We are starting with this month on image data, file formats, and image data management, talking about current state and challenges. Now it's not advancing. So this is going to be chaired by Beth, whom some of you might have seen when you have attended further events of the series. And we also would like to thank the Bode Institute for providing the infrastructure for this seminar series. I would like to make you aware of the fact that you can actually follow GloBIAS on LinkedIn and Blue Sky, and you are invited to go there and check this out. And if you want to become an active member and help us shape the future of bioimage analysis, check out our webpage, and there you'll find a join as a member button, and you can check what the benefits are and the membership fees you would pay. We have a kind of tiered system depending on where you sit and whether you are a student or already a scientific employee. So our seminar series is meant to provide a dynamic platform for bioimage analysts, and we really want to enable the community to stay up to date with the latest developments in the field. It's designed to cater for intermediate and advanced scientists and analysts, and we want to provide a practical content and not only basic instructions. We usually record the seminar and there usually is also an image SC thread, and as far as I heard from our speakers today, they already have image SC thread for this topic, so slides might be linked in there and you can ask questions there. The recording goes up on YouTube once they have finished editing. Usually it takes about 2 weeks. So that's all from my side for the moment.
Cool. Shall I kick off then, Beth?
Yeah, please get underway whenever you're ready.
Awesome. So thanks everyone for coming to the last seminar of this year. I'm just going to go ahead and share my screen. So I'm David Stansby, hi, and my colleagues Kimberly and Rory are also going to be chatting a bit later when I work out how to minimize that. Okay, cool. Hopefully you can see our eyes. So yeah, Rory and Kimberly will be talking later. And we're going to be chatting about handling huge imaging data with OME-Zarr. And so some of you might have heard of OME-Zarr, the data format. Some of you might be experts in it. Some of you might have just heard of it and be interested about it. The idea of today is we are going to go very quickly over what is OME-Zarr, give you some examples of creating and datasets using Python. And this is all based on a digital textbook we wrote this year as part of a grant, which I'll tell you about a bit. So I always like to start off with a nice bioimaging image. So this is a 2D image of a 3D scan of a heart, which is about 6 terabytes in size, the whole 3D image. So this is one of the reasons why I'm so interested in this area. So the project we were part of was called Hefty, which stood for Handling Enormous Files from 3D Imaging Experiments. This acronym is the peak of my scientific career coming up with this. Nothing will match this, I think. So I really enjoyed coming up with that. And this was an EU-funded grant to develop training and tools for handling big imaging data sets and really focusing on OME-Zarr. So myself, Kimberly, and Rory there in the bottom left with a team from UCL And then Norman on the right there from Scalable Minds was also involved in the grant with some of his colleagues. And they developed WebNosos that you might have heard of. And he's going to be talking at the next GloBIAS seminar on the 26th of January about WebNosos, and that'll include some of the work he and his colleagues did on this grant to add more features to WebNosos. So, as I said, we're going to talk about this digital textbook that we wrote. It's available there at OME-Zarr-book.readthedocs.io. And afterwards, you can go and read that. It goes into a lot more depth than we have time for today. And the examples that Ruaridh and Kimberly will show you later are all in there, and you can download the code and run it. Perhaps try running it on some of your own data. So just to give you a bit of context for why we're so interested in this, if you go to a hospital and have a CT scan, this is what it looks like. So these are my lungs. The resolution is about 1 millimeter. And these are 3D images. So you can see a 3D rendering in the bottom right and a slice of that on the screen. And in total, this CT covers most of my body, and it's about 200 megabytes in size. And my laptop has 8 gigabytes of RAM, right? So it's super easy to just load this into memory, do whatever processing I want, and I don't really have to worry about how big the image is. So this is a clinical kind of image, but if we're doing science and we go to a much more fancy kind of detector, this is what it looks like. So the project I work on, we scan human organs at a synchrotron using X-ray phase contrast imaging. And these are all available as part of the Human Organ Atlas. And you can see this kind of remarkable detail. So if I flick back to this blurry image and now forward to this really high resolution image. And, with all that detail comes extra data size. So this 3D image is 500 gigabytes. So at this point, I can't just load this onto my laptop. And even if I have a really high-end desktop, I might have 64 gigabytes of RAM. If I'm, if I've got a really big grant, maybe I can afford 256 gigabytes of RAM. But I still can't just load this image all into memory at once, which really changes how we have to approach loading and processing these data sets. So how are these 3D images typically stored on a computer? So a really easy and simple way to do that is you can take a 3D image and you can split it up into lots of 2D planes. So each cube here represents one pixel or voxel in our image. And here, each color represents a different file. So, for example, if you split your 3D image up into PNG files, you could start at the top and label the first one 0.png, the next one 1, the next one 2, and so on all the way down. And this is a really nice choice for lots of reasons, right? So 2D images are everywhere in the world. So the technology for displaying them, processing them is super, super well developed. You can really quickly look at a PNG image just on your computer without installing any specialized software. And you can just send that to someone and, they can open it on the phone and with no problems. So this is great in many ways for storing, but when we have really huge images, we start running into some problems. So let's say I want to just look at the 4 pixels or voxels that are in orange here in the center of the screen. If I store every slice of the image as a file, I have to open, in this case, 2 files, and I have to open all that data, but I only want 4 pixels. So I end up opening these huge slices and throwing away most of the data just to get at 4 voxels or pixels. And so this can be very slow if the data is compressed. So, if you're using JPEG images, maybe you might compress your data quite a lot. And opening the data can be very slow. And it also takes up a lot of memory. So the images I work with are typically would be more than 100 megabytes a slice. So I'd have to load in huge slices just to throw away most of the data. So to give you an idea, if I want to load a cube of data that's 128 by 128 by 128, that's about 4 megabytes. For one image in particular that I work on, I'd have to load in slices that are 9,000 by 9,000. I'd have to load 128 of those, and that's 20 gigabytes, right? So I'd have to load in 20 gigabytes and throw away almost all of that just to get at 4 megabytes of data. So one of the solutions to that really is storing images as chunks. And so the idea here is, instead of storing every file as a slice, you instead choose how to split up your data and save that to files. So in this example, each color again represents an individual file that would be saved on your disk. But instead of splitting the image array up into slices, I've split it up into 2 by 2 by 2 chunks. And this is really nice, because now when I want to load that 128 cubed cube, I only have to load maximum 256 by 256 by 256, which is 33 megabytes. And so we've really made a big saving there in terms of how fast it is to access that data, and how much data transfer we need to do. If we're looking at these images over the internet, that's a huge difference. So this is what Zarr is. So the Zarr part of OME-Zarr is basically this idea that you take an image or a data array, you choose what the shape of the chunks is you're going to split it up with, and then you save each of those chunks to individual files. So I've represented that with this little flowchart at the bottom. So you take your array data, split it up into these chunks. You can then add compression to those chunks, and so to reduce your file sizes, and that is typically at the moment in Zarr lossless compression. And then you save that data to file. And so, yeah, that's a really high level overview of what Zarr is. Hopefully we won't talk about it today, but the way I've drawn this diagram at the bottom hints that you can process each of these chunks in parallel, which really opens up a new world of being able to parallelize your data and run your processing algorithms at a big scale. So with Zarr, we've really solved this problem of, how do we, when we're looking at our data, make sure we're not loading more than we need at any one time. If we have a big array, we also have this other problem that if I want to look at the entirety of my image, so this slice I showed at the beginning in full resolution is 12,000 by 13,000 pixels. And so that's 161 megapixels and about 300 megabytes. But the screen I'm presenting from at the moment is only 3.6 megapixels. So if I was to load that whole 300 megabytes of data, I'm not actually looking at each of those individual pixels, and that's a bit wasteful. So one way we can do this is, as well as storing the full resolution data, which I've represented on the left here by this kind of 3D stack of cubes, we can also store downsampled copies of the data alongside. So as well as storing full resolution, we can bin it by 2 and bin it by 4 and so on. And then when we want to look at this whole overview of the data, we only have to load an appropriate zoom level. And then as we zoom into the data, we load higher and higher resolutions, but only in our field of view. So a really good analogy here is Google Maps. When you're looking at the whole globe, say, it doesn't try and load every single street in the world. It just gives you that overview. And as you zoom in, it starts loading more and more information. And eventually you zoom in and see your street right at the end. So this is exactly the same concept. We start at low resolutions, and as we zoom in, we load that higher and higher resolution data. So that's the OME bit in OME-Zarr, really. So OME-Zarr is this multi-scale image storage where we use Zarr to store each individual array, and then we store the full resolution alongside lots of lower resolution copies. So this is a data specification developed by biologists for biologists, and it really enables you to visualize and process data at a vast scale. So I'm going to finish this section of the talk with a little demo of what that enables. So I'm just going to have a quick sip of water. Okay, so this is the Human Organ Atlas, and I've just chosen a uterus data set here. I'm just going to show you the visualization of this. So I have no special software installed. This is all in browser, and this whole data set is about 400 gigabytes, I think. And already, as I was saying, that the data has loaded. So you see the three orthogonal planes. I have a little 3D view in the bottom here. And this has loaded that low resolution data. So really quickly, I get an overview of the whole data set. And then I'll demonstrate the second feature, which as I zoom in, hopefully if my internet holds out, yeah, you can see that it's loading that higher resolution data. And so for us in my research group, this is a super powerful, and OME-Zarr really enables this, which is being able to visualize this huge data set at high resolution with no special applications installed, just in the browser. Cool, so I'm going to finish my first part of the talk there. I'm going to hand over to Kimberly, who's going to take you through an example of creating an OME-Zarr dataset. Thank you.
Okay, great. I will share my screen. All right, hopefully you can all see this now. All right, so the idea is I'm going to take you through some of the code we have in the chapter in the book about creating new Zarr arrays. I want to stress this is going to be a kind of cut down, fast tour through what's available in the chapter. So don't worry if you don't fully understand every single piece of code I'm going to be showing here. The idea is really to give an overview of how this process works and what goes into it. And then the book is there if you want to go through it in detail, run the code yourself, etc. All right, so first important bit is we set up some helper functions, which will allow us to load some sample data and also plot slices through that data. We're going to be using some data from the Human Organ Atlas that David just mentioned. And if I run these first two chunks, you should be able to see a slice through it. So this is the data set we're going to be using. It's a 3D image stack of a human heart. And what I'm doing here is I'm just plotting one individual slice through it, but the real thing is the full three-dimensional volume. And what we're going to look at is how can we convert this image that might be in a standard file format like TIFF or something equivalent, how can we convert that to Zarr and then into OME-Zarr as well further down the line. All right, so starting with Zarr, the first thing I want to say is there are lots of different libraries in Python for working with Zarr and OME-Zarr datasets. A lot of these will have convenience functions where in 1 or 2 lines you can take your image, convert it, and it will use appropriate defaults. We're going to take a slightly more manual approach here where we really go through every step so you can see how the metadata gets set up, the exact structure of everything, and so on. But just bear in mind that there's a lot of libraries out there to explore. All right, we're going to be using Pydantic Zarr, which is a particular library in Python for creating Zarr metadata and validating it. We're going to be using something called an array spec. So array spec is short for array specification. You can think of it as short for metadata about our Zarr arrays. It's a way of defining, for example, how big we want it to be and what data type you want it to have and all of these other aspects. So that is then what I'm doing down here. So I'm taking this array specification and I'm defining those common attributes, things like the shape, which will be the size in X, Y, and Z, because this is a 3D image. And here, because I'm using an existing image and want to convert it, I'm setting it to be the same as the shape of that heart image. Then I have the data type. So this is, do I want it to be 8-bit? Do I want it to be 16-bit, etc.? Again, I'm using an existing image, so I'm going to set it to be the same. And then we have the chunk size. So this is what David was just talking about. This is the fundamental concept of Zarr. Everything is split into these smaller individual chunks, which will be the files that get saved on our file system. And this is how we set the size. So in this case, I'm setting it to be 32 by 32 by 32 voxels, but you can set it to whatever size would be appropriate for your specific data set. Final thing we're going to be setting here is the compressor. Don't worry if you're not super familiar with compressors. They're tools that are used to help reduce the overall file size. There are many out there. We're using ZSCD here with a specific setting, which is the compression level. Potentially, we might mention that briefly later with the benchmarks, but again, there's more in the book and so on if you want to get deeper into this. All right, so if I run this, you should see a summary of everything I was talking about. And again, this is metadata about what we want our array to look like. Things like the shape and the chunks and the data type and some other values, which I won't have time to go through right now. So we have our metadata, but so far we haven't actually created anything. We don't have our actual array yet. So to do that, we're going to be using another Python library, which gets imported as Zarr. And this is Zarr Python, which is one of the main libraries for interacting with Zarr arrays in Python. In order to actually create your array, you have to define where you want it to be created, and that is controlled by something that's called a store. For the sake of this demonstration, we're going to use a memory store, which will keep everything in the memory of my computer. This is mostly for convenience. It's fast for me to do, and it means I don't have to worry about editing any of the sample data that I'm using. But it's likely if you're doing this with your own data, you'd be using some other kind of store. So something like a directory store, which would let you write to files on your file system, or some kind of store that supports remote access to write to S3 buckets or Google Cloud Storage or whatever your favorite cloud platform is. But for this case, we're going to use a memory store. So I'm creating a memory store here, and then I'm using this array specification I set up here to then write that into an actual Zarr array. And again, I give that store to say, please write that array into this location. If I run that, it will print out to say that it has created the array, it has this specific shape, and it has this specific data type. And we can verify that that worked by plotting a slice from our Zarr array. For people who are familiar with NumPy and how that works in Python, Zarr arrays will work very similar to that. So often you can use them in the same functions. So I was using this earlier with a NumPy array, but there are similar operations available for Zarr arrays. And this is what we see. So we see this black square that's a slice through, and this is actually what we expect to get. Because so far we've created the Zarr array, but we haven't actually put any data inside of it yet. It's just an empty container, you can kind of think of it as. By default, your Zarr array will get filled by what's called the fill value. So I can print that out down here, this Zarr array.fill value, and you'll see that that is 0. And that's why we're seeing this black array. It's all been filled with zeros by default. So the final thing you have to do to actually have your image data inside of the Zarr array is to copy it over. And that's what I'm doing here. So I'm taking everything inside of the heart image, so everything on this side, and putting it into my Zarr array. And then I'm plotting a slice again, and hopefully we should see something more sensible for the output here. Yeah, and then we see our slice through our heart data set again like this. So just to summarize this part, so we made metadata about the array, which was the array spec. We then created an empty Zarr array, which was full of zeros, and then we copied our data into it. So this would be a simple way of converting your image into an individual Zarr array. But again, as David was saying earlier, Zarr and OME-Zarr are slightly different. So Zarr is what's being used for our individual arrays, but OME-Zarr adds extra information on top of that. It adds additional metadata. It also has this idea of having multiple resolution levels, so multiple different arrays. So that's what we're going to do now. Again, there's loads of Python libraries for this, but we're going to be using one called OME-Zarr models, which again has a lot of functions for creating OME-Zarr metadata, validating it, and doing a bunch of other stuff as well. It works very similar to what we were doing before, but now we're using this image that comes from OME-Zarr models, and we're calling image.new, and then we're giving it a bunch of information about what we want our OME-Zarr data to look like and how we want it to behave. So the first row on this is array specifications. So exactly what I was doing previously, But now the advantage here is we don't only have to have one, we can have multiple for different resolution levels. For the sake of demonstration, I'm going to start off having one, and then we're going to add a few more later. So yeah, here I have my array specifications. At the moment, only one, the whole full resolution data. I can then give paths. So these are the locations of the various data sets. Again, to start with, we're only going to have the one here. And then we define some of this extra metadata that comes with OME-Zarr, which is various things that are useful for image data. So here I'm defining what axes I have. I'm saying I have X, Y, and Z axes because this is a 3D data set. I can say that these are spatial axes rather than time or something else like that. I can give their units and so on and so forth. I'm setting the scale here, so the size in real world units. I've set this up here for the voxel size. And then you can also specify various translations and so on. For the sake of simplicity, we're going to leave these as default as possible. And then finally, give it a name. Here we're using a heart image, so we'll call it heart image. If I run that, you see a lot of data here. Again, don't worry if you don't understand the details of all of this. The important thing is this is metadata about our OME-Zarr image. We're saying how we want it to appear, what size it should have, and so on and so forth. And at the moment, we're saying I want it to have one data set inside, which will be the full resolution data. As before, at the moment, we kind of have metadata, but we haven't actually created anything yet. We haven't created our image. So here we do exactly the same thing. We're going to make a memory store again, and then we're going to use OME-Zarr image.toZarr to take all of this and create an empty OME-Zarr image now, which will also be filled with zeros by default. We can verify that by pulling out the array from this. Again, don't worry too much if you don't understand all of this exact Python context. It's all in the book if you want to go through in details. But here I'm getting the group, and then I'm pulling out the specific location of that array. And then I'm going to print out everything that's inside of that array. And as you can see, it's filled with zeros. Again, this is because of this fill value. We haven't actually put any data inside of here yet. Okay, and then that's the final thing we have to do. Very similar to what we did before. I take all of my values from this star array and I'm going to put it inside of my OME-Zarr image, and then I'm going to print out the values. And you see now we have actual numbers inside of here, and it's worked. All right, so this bit, we now have a full OME-Zarr image with all of the right metadata and so on and so forth. But at the moment, it only has one array inside of it, which is the full resolution data. And as David was saying earlier, one of the really powerful things that OME-Zarr adds is this ability to have multiple resolution levels that we can swap between when we're zooming in and out, for example. So now I'm going to show you a very quick example of showing multiple data sets inside of this as well. So first of all, we can look at the one data set we have. So far, we only have this one, which is the full resolution data. And now we need to make array specifications for each one of these data sets. So what I'm going to try and make is an OME-Zarr image that has 3 data sets inside, the full resolution data, a sort of middle resolution one, and then a low resolution data set that we can swap between. So I'm pulling the full array specification from earlier. If I print this out, you should see it's exactly the same as before. This is, the shape and the chunk size and so on and so forth. And now what I'm going to do is make downsampled versions of that array specification. I'm going to make 3 levels. So like I was saying before, a full resolution, a middle resolution, and a low resolution. I'm going to call them 0, 1, 2 in this case. And I'm going to take this specification and update the shape to be these smaller sizes as they go. Again, I don't have loads of time to go through the details here, so I'm just going to run it and then show you what the output of this is going to be. So now, rather than having one array specification, we have 3 for our high res, middle res, and low res. And the important thing you can see that's been updated is the shape. So the full res is 120 by 120 by 139. My middle res is 60 by 60 by 70, so about half the size of the previous. And then my final one is 30 by 30 by 35, so about half again. So we kind of have full res, 2 times downsampled, and then 2 times downsampled again. All right. Again, we then have to specify the metadata for our whole OME-Zarr image. But the difference now is rather than giving that one array specification, I'm going to give all 3 that I just created. So again, I'm doing image.new, but now I'm giving all 3 of those. And then all of the updates I've made here are really just to provide something for each of those data sets. So now I have one path for each. I have one scale for each, one translation for each, and so on. If I run this, again, you get lots and lots of information. The important part is we now have 3 datasets, which are our 3 resolution levels, and we have 3 array specifications, which are going to be our 3 arrays. Okay, and then exactly the same as we did before. At the moment, we have metadata, but we haven't written it anywhere. We have to create a memory store, and then we have to call toZarr to actually write into that location. All right, I've run that now. So now we have our OME-Zarr image, but it's full of zeros. We have to actually put data inside of this. And that's what this final part here does. Again, slightly complicated code to go through, but the summary of what it's doing is it's taking, first of all, the full resolution, which is what we're doing here. This is exactly the same as I did in all the previous ones. I take all my data, I write it into the full resolution. And then what all of this is doing is it's taking each of the downscaled levels, reading the scale I want. So, do I want to downsample by 2 times? Do I want to downsample by 4 times, etc.? Then it's downsampling my image with this function. There's lots of different ways to do this. SciPy is a very popular Python package for this sort of thing. And then I'm writing that downsampled image into the correct place. So this is really filling up those arrays. I have 3 empty arrays of different sizes, the full res, the middle res, and the low res. And here I'm writing the full res, then I'm downsampling it 2 times, putting it in the middle res, downsampling it 2 times again, and putting it in the low res. All right, so final thing, just to prove that that actually worked, I can pull that out and then I can plot the lowest resolution data to prove that it's actually been downsampled. Okay, so with this, we can pull out the level 2 dataset, which is the lowest resolution one. It says, hey, here is this dataset with some information. I can pull out the actual Zarr array from inside of that again, using the path. It will think a bit and then it will complain. Why? Oh, I didn't run this. As everyone knows with Jupyter Notebooks, it's really important to actually run all of your cells, otherwise it doesn't work. So here it's actually written it, I run it, I get my array, and then the final thing I do is I plot out this slice. So this is the absolute lowest resolution dataset, and you can see it has actually downsampled it. All right, so very quick whistle-stop tour through this. Again, I want to stress you don't have to understand every part of this. It goes through it much more in detail in the book. But this is how you would take an image, make it into a full OME-Zarr image with all of the metadata, and also with 3 different resolution levels that you can freely swap between. With that, I think I'll stop there and I'll pass over to Rory, who's going to talk a bit about exporting data from OME-Zarr images.
Thanks, Kimberly. I'm just going to share my screen. Yeah, so my demo will be more about exporting data. We'll look at how to convert volumes of Zarr images to other file formats. There's a 3-step process allowing you to extract subvolumes of large images into different file formats. Step 2, perform some analysis or processing on the data. And then finally, copy the results back in place to the original Zarr. Just a quick note that this demo only works with individual Zarr arrays. The process is more complex for OME-Zarr. As you see from Kimberly's demo, you need to have a series of different resolution levels. And that affects the subvolume because you need to ensure that the resolution levels are updated correctly. So yeah, so for this demo, I'll be converting Zarr subvolumes to TIFF. And to start with, we'll load our heart sample dataset as a Zarr array and then extract a smaller volume as a NumPy array. So yeah, similar to Kimberly's demo, we have data helpers load heart data and plot slice. So I'm just going to run this and just print out some information. So at the moment, the Zarr array is on disk in a directory store. The shape is 120 by 120 by 139. Data type is there, and the chunks are 64 by 64 by 64, and the array size is about 2 megabytes. So this lazy loading approach is one of the key advantages of Zarr. You can work with arrays much larger than your available RAM. So for the OME-Zarr book, we don't want to modify the copy of the data stored on disk because it is used in other chapters of the book. So for this demo, we'll create a copy of the array in memory. Again, for large arrays, this might not be possible. Yep, so you can see now the new Zarr array is now a memory store object. So now let's extract a small subvolume from the Zarr array. And this will only load the requested slice into memory as a NumPy array, leaving the rest of the data untouched. So here you can see that the subvolume has now gone down to 50 by 10 by 7. And originally the data was 2 megabytes for the full data set, and the extracted subvolume is only 0.004 megabytes. The next step is to write this NumPy array to a TIFF file using the image.io library. And on the side of my screen, an image file has now been created, which I can now open up on my laptop. Yeah, and this basically has the 50 slices in a 2D representation. I won't go through all of them, but you can see that there. If I want to open it up in a 3D representation, I can use an image viewer such as Nupari. So here I've got Nupari opened up. I can do open files as stack and open the TIFF file. So again, the 50 slices are shown in a 2D representation, but you can also see the 3D representation. So this is our subvolume shown in 3D. So at this point, some processing can be done on the subvolume TIFF files. So for this demo, we'll fake processing by creating a subarray of the same shape as the original subvolume, but filled with zeros, and then using, again, the image.io library to read the TIFF file back into a NumPy array. So yeah, here we read in the image file.tiff, and here we use a Zarr method called zeroslike to create the fake processed array subvolume. This NumPy array can then be copied back in place of the original Zarr. So yeah, so this is the original Zarr, and then in the same coordinate space that we had for the subvolume slice, I copy in my process subvolume. Then finally, the following two plots show the original data still stored on disk and the modified data stored in memory. And then in the modified data, you can see the change. So for this, I'm plotting slice 45. So this is the original data. And in the modified data, you can clearly see this black rectangle in the center of the image, which is our subvolume that's been processed and placed back into the Zarr array. And I think I'll hand over back to David now.
Brilliant. Thanks a lot. So yeah, so we've gone really quickly there through 3 chapters in the textbook. So the first one was kind of an introduction to what Zarr and OME-Zarr is, and how they work, and what advantages that brings. Then how to create an OME-Zarr dataset, and how to export subvolumes of that dataset to kind of more traditional file formats, do a bit of processing, and load them back in to your Zarr array. So I'm going to finish with a couple of things now. So one of the other things we did as part of this project, which I won't go to in detail, is we did a bit of benchmarking. So you'll have seen when Kimberly was creating the OME-Zarr arrays, there's lots of parameters, kind of lots of knobs you can tweak when you're creating those data sets. And that includes the size of your chunks. And it also includes how you compress the data. So for data compression especially, there are lots of different compression algorithms, and even within individual compression algorithms, you can tune those with different parameters. So we also, Rory and Kimberly also did a really nice job of doing benchmarking of all these options, so you know which of these options give you better data compression or faster write speeds or read speeds. And we have a little report that we wrote up about this that might be able to help you choose the parameters for your Zarr arrays. So I'll stick the link in the chat afterwards. So I wanted to finish with a bit of a where we're going next with the textbook. So this really started out as part of the Hefty project, but we renamed it from the Hefty textbook to the OME-Zarr book, because we really want it to have a life beyond our project. And as part of that, we'd really love to see community input. So if you spot any problems with the book, if you have any suggestions for stuff to add, or even if you want to write new material, we'd love input from the community. In terms of concrete things we'd like to add to the textbook, so everything we've shown you and talked about today is using Zarr version 2 and OME-Zarr version 0.4. Some of you will be aware that they're not quite the latest versions. There's now Zarr v3 and OME-Zarr 0.5. So we'd really like to update the textbook to these newest versions. In terms of chapters, we'd like to add new chapters on containers that are within OME-Zarr. So for example, how do you store high content screening or image label data alongside your original images? And the big new feature coming to OME-Zarr soon is coordinate systems and coordinate transforms. So we want to write a new chapter all about that. And then the parallel processing and exporting chapters, we'd really like to expand. They're a little bit threadbare at the moment. They cover the basics, but there's lots more we could explore in that. So yeah, we would love to expand the textbook. Super welcome contributions. We're also on the lookout for funding. We could apply for to do this. So if you're aware of anything and would like to see any of this, please let us know. We think this textbook is a really great example of what a solid bit of funding enables, and we think this really fills a gap in educating people about how they can use OME-Zarr for their data. So I'm going to finish there because I see there's a few questions in the chat that hopefully we can get to, but just to say thank you for coming along. The textbook is here. I'll put the link back in the chat. Thanks to the EU for funding us, and any questions that you think of afterwards, feel free to email me on my email address. Thank you very much.
Thank you, folks. That was wonderful. I already sent the textbook back to my Slack channel for folks at home. All right, yeah, we do have a bunch of questions in the chat. I'm gonna try and maybe start some simpler ones and work our way up. What happens when you're working with chunks of the data? What happens if a filter is run on the edge of the chunk? So for instance, when using a median filter kernel.
So in that case, you would have to be careful that when you're running the filter over your chunk, so you'd run the filter over your data, you just have to be careful that you're loading in all the chunks you need to apply that filter. In Dask, they have this concept of like, when you run a filter over, you load the chunk in the middle, but also all the ones that are around the edge as well. So yeah, it's something you definitely have to be careful and be aware of, but there are frameworks out there that will handle it for you automatically.
Great. An excellent segue into another question, which is, you talked about parallel processing on Zarr arrays. Is that possible with NumPy, SciPy, or do I need to use a different library for that?
So NumPy and SciPy don't have built in the tools for you to do parallel processing. So you'll probably have to find another library that would use NumPy and SciPy underneath, if that makes sense. So yeah, popular choices in Python are Dask, which I mentioned, or I use a a library called joblib as well, which kind of allows you to do parallel processing quite nicely. And joblib is the library we use in the textbook in chapter 3, which we didn't have time to cover.
And are there tools other than Python and Jupyter notebooks that are available to work with Zarr files?
I am very much a Python person, so not the best person to answer that question. I don't know if Rory and Kimberly, you want to jump in and have any suggestions?
Yeah, I mean, I guess I can talk a little bit from the ImageJ sort of Fiji side as well. So there's also support from OME-Zarr there. I think you've always got to find the particular plugins that support it. So it's not like you could load it and immediately apply anything again, because it has to be something that properly supports handling chunks in the right way, and like we we're talking with filters, making sure it's being handled in a sensible way so that you don't get artifacts. But in terms of viewers, there's things like Big Data Viewer in Fiji, which has really nice support for OME-Zarr. Things like Big Warp, etc., will also support it as far as I'm aware. So yeah, Fiji as well also has a lot of support. I'm sure there are other tools that are also starting to support it, but it's something that's gradually growing in support. So it's always worth looking at a library that you're interested in, have a browse in their documentation, see if they're supporting it. And otherwise, the image.sc forum is a really great place to, if you're looking for a very specific kind of processing, do post on there. There's loads of people who are deeply involved in OME-Zarr that are on there that will be sure to help you out and give some suggestions.
Thank you. We have a couple of questions around chunk and block size and how you set them depending on the underlying file system. Is there a way that you set them based on what you're going to do with the data that you're processing later? How do you think about setting those parameters?
Yeah, so in OME-Zarr 0.4 and Zarr v2 certainly, there's kind of this trade-off between, so for every chunk you have one file, which can mean you end up with like hundreds of thousands of files that can really become an issue on some file systems. So that's something to be aware of. In terms of chunk size, think about what you're planning on doing with the data. So for example, if you want to visualize the data over the internet, you kind of want smaller chunks, say 3-4 megabytes, because you want, data transfer speeds are slower than just on your computer. So you want to be able to see some data, quickly. So choosing 3 or 4 megabytes is a way to enable some of the data to show up quickly. If you're doing processing locally and you have, I don't know, say 8 gigabytes of RAM, you probably want to choose a chunk size that's a lot bigger than a few megabytes, because for every chunk there'll be some overhead in like setting up tasks and processing the chunk. So yeah, we typically choose chunk sizes of about 1 or 2 gigabytes at the point where we're processing the data on our computers and not usually using it over the internet. And also, I would also say experiment, right? You take a bit of your data and try out different chunk sizes and see what works best for you, because, hardware and situations are always different.
Great. We have a couple of questions around sort of sampling and anisotropy. So how does it handle whether the image is XY or XZ acquired, in case the Z dimensions are acquired with a different step size, and are there best and common practices for downsampling, especially if your voxels are anisotropic?
Yes, you can have different. Kimberly, I don't know if you could show the creation notebook and the stage at which you show where the scales are defined. So you can set a different voxel scale in each dimension. So in our examples, we just use an isotropic size, but somewhere in here.
Yeah, I'm just trying to find where it is.
Yes,
Here
yeah,
where
exactly.
the
So here, where you see the scales list, or yeah, the voxel size here. So you could change those three numbers to different. So you could have two of them the same, say for X and Y, and in Z, if you have a different spacing, you would just change that to a different number, and that would account for the different step size. That was a question about a different step size in Z. I feel like there was another question as well that I've
around
forgotten.
downsampling. So can you also set the downsampling to happen differently based on the different anisotropies or?
Yeah, you can. The way we did it here, it just downsampled the same in each dimension, but you could, when you implement your own downsampling, you could change how it downsamples in the different dimensions.
Awesome. Very important question, versioning. How can you version the data sets that that you're making with OME-Zarr?
So I think, and my understanding is that OME-Zarr does not address versioning datasets by itself. I think, yeah, I think it doesn't address versioning. Someone feel free to correct me if I'm wrong on that.
I don't know of anything it does natively, but there are definitely things out there like the Data Version Control or DVC project that are things that you can look into in terms of versioning large-scale data. I've never personally tried that against OME-Zarr, but since each thing is its own file under the hood, in theory, I believe DVC should work with Zarr. What is your advice in running segmentation in scaled data sets? Could you keep the segmentation for the full res data set together with the original data set, or is it advisable to keep separate processed and raw data?
Yeah, great question. So we didn't talk about it because it was one of the items on our roadmap, but OME-Zarr does support storing image labeled data sets next to the original image data. So there's a special directory in the Zarr group for segmentation or label data sets. So yeah, I say definitely advisable to store it alongside the raw data so you have that link and you know that the labels would derive from that raw data.
Yeah, and we got a question. I apologize. I didn't really define versioning. Versioning in the sense of we've seen some great examples here of, running processing, or in the same way I just mentioned, you might do some filtering or things like that, or segmentation. How do I, if you're saving that into the same Zarr container file, which is nice to have from the and being able to say, here are all of the things that sort of go together. How do I make sure that I didn't overwrite my raw data with my process data? Or how do I simply know that if I sent you the data a while ago, that your, OME-Zarr file that has the same name as mine actually contain the same bits or not? So apologies for not explaining that. Thank you
Yeah,
for.
no, that's a great question. I think beyond just opening the data and looking at it, there isn't any mechanism for like verifying the version of the data, if that makes sense, or seeing if the data has changed. And in terms of making sure you don't overwrite the data, I guess when you're writing your code for processing, making sure that if you don't want to override your data, always make sure you're creating a new OME-Zarr image and you're reading from one image and writing to another image. You kind of just have to make sure you're doing that. And I guess one way that helps is when you open your image, you can open it in read-only mode. So that ensures that if you accidentally write a bit of code that tries to write, the software will say, no, you open this in read-only, you're not allowed to write to it.
Right. Now to our couple of questions. OME-Zarr compression use GPU?
That will depend on the library you're using to read and write Zarr files. I think in Python, at least, the answer is there isn't any support at the moment, but people are talking about it. For other Zarr libraries, I don't know.
Folks, if you do have more questions, we have a couple more minutes, but last question that we have in the Q&A box for now. Are all of the notebooks that you've shown today in GitHub project the text?
Yeah, so they're not Jupyter notebooks. They are, I'm having to remind myself now, Kimberly and Ruaridh, I don't know if you want to jump in, if you know, can remember off the top of your head the easiest way of like downloading and running the code. I'm just reminding myself. So maybe we need to add a download as a Jupyter notebook button to our website.
I think at the moment they're all in there as markdown files. I think there's a bit of a description in the README, but it's more aimed at developers for how you can open those files directly inside of Jupyter Notebook and run them through Jupytext, I believe, if I remember. So I think that does work, but yeah, you're right. We could have an extra section there, or providing some way to download them directly as Jupyter Notebooks might be a good idea. Yeah, at the moment for these ones, all of the code is stated in the chapter, and I just took out the pieces I wanted to use and put them into a separate Jupyter notebook. So, yeah.
Great. Is it possible?
You're muted, David, if you're speaking.
I will put a link to the markdown files that has the code. Thank you. Beth, I think you're muted now.
Is it possible to convert whole slide images from proprietary formats like MRXS into OME-Zarr directly?
I do not know. Kimberly or Rory, do you know?
I know for Amero, it's got bioformats inbuilt, but this is maybe not accessible to everyone. Amero is like an imaging viewer and data management platform, which can handle OME-Zarr data. So yeah, when you upload your data to an Amero server, you can, probably convert proprietary file formats into OME-Zarr. But I don't think Amero's got a web-based version of it itself. So yeah, don't know how easily accessible it is to everyone. We have an Amero server at UCL, but yeah, not everyone does.
Yeah, I was just going to say that there are a lot of different libraries for converting to Zarr, so it's worth having a browse around. I haven't tried it with that specific file format, but there is something like bioformats to raw, which supports a really wide range. I think I'll put a link in a minute, but there's a list in the NGFF documentation where they list a whole bunch of different converters, and it's worth having a look there and seeing if one of those supports your specific file format.
I think we might also have that in our book as well, if I remember correctly. Suggested converters.
All right, we are right up against the hour, so if there's we have a couple more now coming in, so maybe those we can transfer over to image.sc or future things, maybe future things that go into the textbook. But thank you everyone for a really fantastic webinar. We really appreciate everybody coming. Thank you for everyone who's participated in any one of 2025's GloBIAS seminar series. It's been lovely to have you. Look forward to seeing you all next year for further talks in this sub-series. But thank you so much and hope everyone has a great end of the year.
Thanks a lot.
Thank you.
Bye, folks.